Great news! The files for 3D printing Flora, my do-it-yourself open source project, are finally online! In today's video, I will show you where to download these, which kind of filament I recommend, how to set up your 3D printer for watertight prints, and what to do if something went wrong. Let's go! If you don't know about Flora yet, I suggest you watch the introductory video first by following the link in the corner and then coming back to this video. After 9 prototypes, I now have finished the first design of my smart self-watering plant pot. It's optimized for printability and watertightness. You can find the download link to Thingiverse in the video description. Getting your 3D printed parts watertight can be quite challenging. Often there are tiny little gaps or imperfections between the filament tracks or layers where the water can leak through. But obviously this is kind of bad for a plant pot that is supposed to hold water. I have a few important tips on how to achieve water tightness, so better watch this video until the end before printing a sieve. If you don't own a 3D printer yourself, maybe there's one at your university, school or workplace that you can use. Or maybe you have a friend that can help you out. I will also try to provide a solution in the video description for anyone else who doesn't have any of these options. Some of you have already asked when I will finish the bill of materials. Right now I'm still making changes to the circuit board, the electronics and the microcontroller to make them work perfectly. But I hope to get this done along with the next video within the next 4 to 6 weeks. So make sure to subscribe to this channel and hit the alarm bell to not miss the release. How to get your 3D printed parts watertight? Unfortunately, there's no simple answer to this question, which is why I'll explain it in 5 sections. I will talk about the right filament choice, print settings, slicing, post-processing and how to make changes to the design. Let's start with the material choice and compare some filaments for printability, price and how they perform when exposed to water or soil. In FDM 3D printing, probably the most common filament types are PLA, ABS and PETG. When it comes to watertight 3D printing, some people also prefer PP. Therefore, I have included this in the list as well. PLA is probably the most common filament. It's usually what beginners start with, since it's very cheap and easy to process. It doesn't even require a heated print bed, so that's your go-to filament if your printer doesn't have that. But especially for this use case, there are some disadvantages. Like many other materials, PLA absorbs moisture or water over time. That's bad because it could eventually distract the soil moisture sensor. Additionally, it's biodegradable, which means that it will dissolve in soil or water. That will take several years. But if you want a really long-lasting plant pot, I suggest you use a different filament or put some protective coating on it. I will talk about that later in this video. ABS is also a very basic and cheap filament, but it's a little bit harder to print. It also absorbs moisture and water, but a little bit less than PLA. Using ABS, you can achieve a super smooth and glossy surface finish when post-processing it with acetone. That will also help to make it watertight. PETG is a variation of PET, which is commonly used for water bottles. That makes it an obvious candidate for watertight prints. Compared to other filaments, the water absorption is really low and it also features a good printability and chemical resistance. The price is a little bit higher though. The only filament I know that is hydrophobic is PP, which is short for polypropylene. Polypropylene? Polypropylene? I really have no idea how to pronounce this in English. Hydrophobic means it repels water instead of absorbing it. Unfortunately, it's way more expensive than the other ones and also quite complicated to print with. Due to the poor layer adhesion, there is also a higher risk of leaks through small gaps in the print. Basically, you can achieve good and watertight results with all of these materials. And if you already have a filament in your desired color at home, I'd recommend simply using that. If you want to buy some fresh filament for this project, I'd recommend to go for PETG, which is also what I used. Or maybe ABS if you want to do chemical smoothing. PP is more suitable for really advanced users if you ask me. In addition, I would suggest not to use transparent filament, as the material thickness is different at some spots, and this would result in darker areas when the light shines through. Now that we have figured out the best filament, let's talk about the print settings. These are absolutely critical for watertight prints, and you probably won't need to do any post-processing at all if you use the right values here. If your printer is fundamentally working reliable, most imperfections and gaps will occur where the perimeter and infill touch or when the extrusion direction changes. That is, when it retracts and then starts extracting again. So we will change the print settings to avoid these things as much as we can. My favorite slicer software is Prusa Slicer, and it's also the one I have the most experience with. So I will use the software as an example and explain all the important settings and show you where to find them in the menu. By the way, you don't need a Prusa printer in order to use their slicer. The configuration wizard comes with pre-built profiles for many printers from other manufacturers, and you can also create a custom printer profile too. If you prefer a different software, I'm sure you will be able to adopt the settings by yourself with the information given. The names of the settings are pretty much the same across the board. I did all my prints with a 0.4mm nozzle, and this is what 80% of all printer users are using mainly. So keep in mind that the 3D model of the plant pot was specially designed for this nozzle size, and the print settings are tuned for that as well. If you would like to use a different size, then you will have to make some adjustments. Alright, here we are in Prusa Slicer. We start by activating the expert mode on the right side to make all the advanced settings appear. Then we open the Print Settings tab and select the 0.2mm quality preset as a basis. After that, it also says MK3, which stands for my printer model, so that might be different for you. Now we are going to make some changes to this preset profile, and therefore we click on the Save icon and choose a name for the new profile. I call mine Flora General. General because later we will create a second profile for a special part. Okay, now for the individual settings. We leave the layer height at 0.2mm. Usually you would choose a lower value for prints that are supposed to look nice. But with, let's say, a layer height of 0.1mm, there would be twice as many layers printed, and between each layer there's a potential gap. So the risk of creating a leak is also doubled. An even higher risk of gaps comes from the contact points between perimeters and the infill. That's why it's a good idea to avoid printing infill where it's possible. We change the perimeter setting to 10, which is a quite high value, to take that into account. This way most of the walls of the plant pot consist only out of perimeters. This also gives us better protection against leaks, because if there is a gap in one perimeter, there's probably not a gap in the same place in all neighboring perimeters. Going on, we check the boxes extra perimeters if needed and detect bridging perimeters. Then in the Advanced Settings tab, I wanted to show you the preset extrusion with values. The values from Prusa Slicer are already pretty good for watertight 3D printing, so we don't have to make any changes here. But for other slicers, I highly recommend changing your settings to match these. By default, the extrusion width corresponds to your nozzle size, which in our case would be 0.4mm. What this setting now essentially does is that the printer will extrude extra material that is squeezed to the sides by the nozzle, creating a larger extrusion width of 0.45mm. This causes adjacent filament tracks to melt together, creating a strong and watertight connection. It might also create some ripple on the surface in areas with high material density, but that's a downside one probably has to take. If you can't find this setting in your slicer software, look out for a setting named Extrusion Multiplier or something similar and change that to 110% or 1.1. That should do the same thing. But remember, don't do that if your extrusion width is already set to 0.45 mm. Another interesting setting is Infill Perimeter Overlap. It does pretty much exactly what the name suggests, controlled by how much the infill pattern overlaps the perimeters. The preset value is very good here again, but for other slicers it might be a good idea to set this to 25%. Alright, we are done with this profile, so click on the save icon again without changing the name to apply the settings. Now we will create another special profile for the bottom part of the plant pot, using the profile we just created as a basis. To do so, make sure the Flora General profile is selected and click the Save button again. But this time change the name to something like Flora Bottom. That is a flat part which needs to be waterproof mainly in the vertical direction and has a few mounting points for other components. Considering this, we reduce the number of perimeters to 3 but increase the number of bottom solid layers to 15. As a result, the flat side of this part is printed completely without infill, which reduces the risk of leaks. To make the mounting points a little bit more rigid, we go to the Infill tab and change the fill density to 30% and the solid infill threshold area to 70 square millimeters. Save the changes and then head over to the Filament Settings tab. Here we are going to create a new profile for our filament. As a basis, select a preset profile that matches the filament you are using. In my case, generic PETG. Now increase the nozzle temperature by 5 degrees Celsius or enter the values from your filament manufacturer increased by 5. This will improve how the layers melt together and reduce potential gaps. Save the changes and give it a suitable name, such as Flora PETG or whatever filament you are using. Now head over to the Printer Settings tab and select your printer. Under Extruder, we reduce the retraction length a bit. I lowered mine by 0.2 to 0.6 mm and got good results with it. If your printer uses a Bowden setup, you should maybe consider an even higher reduction. I also changed the minimum travel of the retraction setting to 3 mm, which will disable retraction when travel moves are shorter than this length. And I disabled Retract on Layer Change. The infrequent and shorter retraction is an important setting in order to avoid gaps, but especially combined with the increased nozzle temperature, this will result in increased stringing. However, these strings can be easily removed, so that's not a huge problem. Save the changes again. I name my new profile Prusa MK3 Flora. And we are done with setting up Prusa Slicer for watertight prints. Finally, I quickly click through all the menus in case someone wants to copy some of the values into their preferred slicer software. You can pause the video anywhere to do so. The most popular slicer seems to be Cura, and that's why I took a quick look at this one too. It comes with some additional options that I haven't tried out yet, but they definitely sound beneficial and I would recommend enabling them when using this program. Under Preferences, Configure Cura and Settings, you can check this box to make everything visible. Now, when you click on your printer settings, in the Walls tab, I recommend to activate Optimize Wall Printing Order and Print Thin Walls. In Cura, I would highly recommend to start out with the Fine preset as a basis and then change everything else, such as 0.2 mm layer height instead of 0.15 mm. This ensures that the acceleration and speed of printer movements are not too fast. Small question. Did you find it too detailed how I explained things so far? I want to make these videos beginner friendly, but also not too boring for others with more experience. It's kind of hard to strike the right balance. Feel free to write your opinion in the comments below. Okay, now it's finally printing time. If you haven't already done so, click on the link in the video description to get to the Thingiverse platform. I would love to see you liking not only this video, but the Flora project on Thingiverse as well. This would help other creatives to find this project and save their plans. There's even a button to tip me if you like my work. Under the Think Files tab, you can download all the 3D files, including the STL files needed for printing. Flora consists of a total of 6 parts, 2 mounts for the battery and water pump, 1 mount for some cables that make up the water level sensor, and 3 parts that form the housing. The reason the housing isn't just a single part is because the inside needs to be accessible in order to mount the water level sensor, and because you definitely want to avoid printing with support structures, as these can easily create gaps in the layers printed on top of them. This also allows for some coating to be applied on the inside of the housing if there should be any leaks. Later the housing parts are screwed together and the joints are sealed with silicone. But before that, some of the electronics need to be mounted, so please wait until the assembly video with this step. For now, start by downloading and unpacking the zip file and then go back to your favorite slicer software and open the STL files. Let's begin with the 2 mounts for the battery and the water pump. I like to print them simultaneously because they can be printed with the same settings and the print time is very short anyway. They do look pretty much the same, but the inner diameters are a little different. Place them upright and close together on the build plate. Prusa Slicer has this arrange button to make this a little bit easier for you. Make sure you have your recently created profiles for print, filament and printer settings selected on the right side. Flora General is the right print profile for this one. As with all the other parts, we don't want any supports or grip, so make sure these boxes are unchecked. Then hit Slice Now and give the preview a final check. The layers should look like this. Afterwards you can export the G-code for your printer to an SD card or whatever you're using. I recommend doing a test print with these small parts to see if there's any need for additional changes in the settings. Same procedure with the inner and outer housing. Place them upright, use the same profiles and no support. The only exception is that it's a good idea to print the outer housing with a brim, as the contact area with the build plate is quite small. The sliced preview for both of these parts should only consist of perimeters, so go through the layers and make sure this is true. If you are wondering what those little walls at the top of the inner housing are, these are custom support structures that I built into the 3D model. So the support option in the slicer should remain deactivated for this part as well. As you can see, they are not connected to the rest of the model, which causes the printer to print them a little bit in the air. This way they can be easily removed from the print later. I did that because I had some issues with the automatically generated support structure from Prusa Slicer in this area. The bottom part of the housing needs to be placed upside down on the print pad and the Flora bottom profile to be selected. This is the only part where infill is allowed for the mounting geometries, but not for the solid part at the bottom. So again, give every single layer a final check. Depending on your filament, this part could be very hard to get off your build plate, as it's quite large but flat. If your build plate is not flexible, spraying some window cleaner on it and wiping it with a paper towel before printing could do the trick. Last part is the water level sensor, which has a few small clips to hold cables. It's designed to be printed in a lying position and doesn't need to hold any water, since it obviously will be located inside the water tank. Therefore, I just used the standard 0.1mm detail profile and the pre-configured printer profile for this part, and I would recommend you to do the same thing in your software. One last tip about the actual printing process. Avoid pausing in the middle of the print and resuming it later. This will most likely create a gap through which water can enter. Speaking of water tightness, what can you do if you had serious problems during your 3D print and now there are visible gaps in your housing parts? Well, you have a few different options here. If you used ABS filament, acetone vapor can be used to smooth the parts. I haven't tried this myself yet, but Prusa made a good video on it. The acetone basically dissolves a tiny bit of the surface of the printed part and then adhesive forces distribute the liquefied material evenly. This will give you some smooth, glossy and hopefully watertight parts, but warping could be an issue. Alternatively, you could get some acrylic spray coating from your local hardware store or apply some epoxy resin with a brush to the inside of the water tank. I've heard that applying molten candle wax could work as well. These three methods are suitable for any kind of printing material. Even if you can't see any gaps in your print, that doesn't mean they don't exist. But don't worry, I will show you an easy way to test for water leaks in the future assembly video. You will still have the opportunity to do the post-processing after that. Finally, let's talk about the last point on my list: changing the 3D model. Unfortunately, you can't simply scale the model by a factor of 2 or so, because then the mounting holes for the screws and hoses and all the other parts would no longer fit. The current 3D model is optimized for a planter with a height of 90 mm, an upper diameter of 110 mm and a lower diameter of 85 mm. This is the smallest size at which the electronic parts still fit into the lower part of the housing. I'll try to add a few bigger versions of Flora in the future, but they will not get any larger than a regular 3D printer build plate. Maybe one day I will create a version for even bigger plants too, but that will require a completely different approach without a 3D printed housing. If you think I am too lazy and would rather like to start adopting Flora to your preferred size right away, or if you would like to change the design as a whole, then you can do so, of course. For that purpose, I have also uploaded the current 3D model in a few different file types to Thingiverse, which can be imported into your favorite CAD software. I did all the modeling with Autodesk Inventor, so the easiest way to change the design would be to use that program too. This allows you to open the original IPT files instead of importing them, which gives you access to this operations menu on the left. Autodesk provides student licenses for their software, so maybe this could be an option for you to get your hands on Inventor for free. Alright guys, that's it for today. Don't forget to like and subscribe. See you in the next video and happy printing! Oh, and if you're watching this video at some day in the future, you can find the next video of this tutorial series over there. And down here is a different video from my channel for you.